All right. Good day, everyone. So, kind of the purpose of today's lesson, and we're going to be kind of splitting 16-1 into 2 days, is to begin to talk about the unit circle. Okay. In today's particular video, we're going to strictly talk about how do we derive values from the unit circle? How do we actually develop those using things like reference triangles, reference angles, applying that to our triangle, and then getting a basic idea of how we can actually use the unit circle to derive answers in a problem. Okay. Note, within this class, the unit circle is going to be essential into solving values out quickly. Okay. This is a tool for us to use to help simplify problems to get specific answers in each one. Now, once we have the unit circle derived, the beauty of it is at any point we can refer back to it to assist us in actually solving values out. Okay. It's kind of this tremendous tool because it gives us so much information in a small piece that we can constantly use. Okay. But like I said, the first step of doing this is we have to be able to derive out certain values. We have to understand where values come from, what they represent, and how they actually come to be within a unit circle. So today's video is simply about creating a unit circle. Okay. What I would highly suggest doing is that if you're creating your own notes or if you're doing something like that, print out a unit circle, draw this out while I go through it. And that way you can really see and have a unit circle at all times. Obviously, at this point, after we go through this day, at any point, you could always Google a unit circle to grab it and actually use it from there. But understanding it is going to be a lot more beneficial than just having it. Okay. So let's just get a blank unit circle to begin with. Okay. Now, the first thing I want you to think about, and the first thing we're going to use is we're going to use very specific degree type measures to help us out to begin this particular problem. Okay. Obviously, at this line, we always have our 0 mark and we also have our 360-degree mark. Okay. Because it is a circle, at some point it's going to start at 0, and then eventually at a full rotation, you're going to reach 360 degrees. If we're going to be dealing with radians, that same value is going to be 0, obviously, or 2 pi. Okay. So now what we want to be able to do is derive certain values going up and down from this graph. Starting with this first corner, understand that this unit circle is going to be broken down into basically 2 different types of angle measurements. The first type of angle measurement is going to be we are going to increase by 30 degrees each time. So we go 30, up here is 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330. Okay. Till eventually we get back to 360 degrees. Okay. That's kind of the first type of reference angles that we're going to use. And we're going to use a 30-degree angle to kind of build off of this. For our radian measures, we want to assume that every 30 degrees is the same thing as 1/6 of a full pi of radians. Okay. So if I'm going to label this out in radians, 30 degrees is also pi over 6. 60 degrees, that would be 2 pi over 6, or in other words, pi over 3. At 90 degrees, we'd have pi over 2. At 120 degrees, we'd have we'd have 2 pi over 3. I'm sorry. 2 pi over 3. At 150, we'd have 5 pi over 6. And at 180, we'd have pi. Now, at the bottom of the graph, it would kind of repeat the same pattern. This one would be 7 pi over 6. Then we'd have 4 pi over 3. Then we'd have 3 pi over 2. Over here, we would have 5 pi over 3. Then we would have all the way over here, 11 pi over 6. And eventually we get back up to that 2 pi value, okay? Those are the radian values of each one going up by pi over 6. But now we also want to deal with the interior versions, okay? In between all those degree measures, we're going to go up by 45 degrees, okay? 45. This one over here, then we go up to 90, then 135. Eventually, we'd get to 180. Back down here, we'd end up getting to 225. Plus 45 would get me to the 270 mark. And then the last one would be 315. Those values are going to be our pi over 4, okay? So this is going to be pi over 4, pi over 2. Eventually, it's going to be 3 pi over 4, converting everything to radians. 225, we're going to create that value of 5 pi over 4. 6 pi over 4 is going to be the 3 over 2. 7 pi over 4 at 315, and eventually we get 8 pi over 4 or 2 pi for that value at the end there, okay? Now, this is just a labeling factor, and we're going to go through in a second and talk about why each of these values represent what they do. Why do we even use this original value of 30, 45, and 60, okay? And then on top of that, I know it's kind of a messy graph, and that's why eventually I'm going to pull up one that strictly relates back to a unit circle graph, but this is kind of the representation I want you to first think about. How we actually go around using degree and radians, okay? Now, one of the most interesting facts that we have to discuss is why do we use 30, 45, and 60, okay? And I think I have a nice drawn out one so we don't have to waste this, okay? So why do we use 30, 45, and 60? Why do we always use those angles in a unit circle? Well, this always represents our special triangles that we use back in geometry. There's a very important reason why we even talk about those special triangles in the first place, is because when it comes to trig, those triangles and the unit circle go hand in hand. What I can actually do is create a triangle, kind of like how we did yesterday with our trig within this circle, where I get a 30, a right angle, which is 90, which means this leftover angle has to be 60. Well, because of that, what I've done is I've actually created an angle in which I can reference all of these values, okay? An easy way I can find them. Now, within a unit circle, we always assume that our radius or our hypotenuse is just going to be a value of 1. So our hypotenuse value is going to be 1 there. So technically, if I look at this triangle, I have a triangle. If I just pulled this thing out, it would look similar to this. We'd have a 1 there, our 30-degree angles inside here, and our 60-degree angles up here. Now, within a triangle or within this value, because it is a special right triangle, I can always reference back to our rules, which in this case, I would always have times the value by x or my hypotenuse. In this case, I don't need to, okay? Our short side or our 30-degree side is always going to be half the hypotenuse. So this value is going to be 1/2. Leaving our 60-degree side based off our rules to be square root of 3/2. What this actually does is it creates a specific measurement at this value, okay? Because I have those two, I can actually relate this back to a specific measurement. Technically at 30 degrees, if I look at this as both an x and a y coordinate, I have the coordinate square root of 3/2 and 1/2. So at 30 degrees, that is the coordinate that reference that. The x value is going to be square root of 3/2. The y value is going to be 1/2. Okay, because we have to assume a unit circle is basically a circle on a coordinate plane. Okay. Now, let's just say I referenced a different triangle. Okay. Let's just say I referenced a different triangle because we know that that coordinate now deals with a 30, 60, 90. What if I reference the 45-degree triangle? Well, based on what we know from our geometry, this also kind of relates back to a special right triangle, okay? Where if my radius is 1, that would create a triangle that if I pulled it out, this would be a right triangle with a 45, 45 equal measures, meaning that each side has to be equal to the square root of 2/2. Okay? Now, what that creates is another coordinate. It creates an x, y value in which I can plot at the top here and always reference that based off those two specific values. Okay? So notice by using our special right triangles, we have specific locations within this graph that we can find and easily reference. Okay? Last but not least, we have our 60-degree triangle, which is actually even better because technically we can always reference back to the 30-degree triangle in this process. Let's kind of talk about what I mean by that. If I were to draw this reference triangle into the actual circle itself, our hypotenuse, base and leg, in which we have a 60-degree angle, a right angle, and a 30-degree angle sitting right there. Well, we always talked about how the short side is going to be the lesser of the two values. Well, now, versus the first triangle we did, the lesser value is going to be my x, and the large value is going to be my y. So literally, for that particular coordinate, I can just flip the x and y values. So if I look at my 30-degree triangle and I flip those two values, technically that's what my 60-degree triangle has to equal. 1/2 square root of 3 over 2. Okay? And just like that, I'm coming up with specific coordinates within this unit circle to help me derive this particular problem. But it doesn't just stop there. This is where the coordinate plane comes into play. Okay? If I took this same exact triangle and basically reflected it over into this quadrant, based off of that information, technically this is 120 degrees right here. But if I drew a reference triangle built into this problem by reflecting the other one over, isn't this the same exact picture but just flipped? We have a 30, 60, 90-degree triangle, which means the actual coordinates of x and y have to be the same, if not similar. The only difference now is we want to reference back to a unit circle and how it's on a coordinate plane. Think about which quadrant this triangle is in now. In a regular unit circle, 60 degrees was in our first quadrant, which means we have positive x, positive y. Well, because the 120 degrees is on the left-hand side now, we are creating a quadrant change in which I am going to have a negative x value because I'm on the left-hand side. So this has to be a negative 1/2 with a positive y value because I'm still up top, creating that angle there. But now, once again, this is where the math really starts to build. Let's just say I didn't even stop there. Let's go ahead and take out this triangle here and use this one here as a reference. Let's just say I jump down to this triangle down here, okay? What if I built another triangle based off of what I see down in this problem and built a triangle that looks similar to this? Well, now, doesn't that look like the same exact triangle, but now reflected over the x-axis? You see how I'm can continuously build these reference triangles within this problem? I'm building the same exact picture, but now it's flipped down below. Well, this actually relates back to the same exact triangle. Notice how it goes 60, 120, we'd reach 180, and then 180 plus 60 would be 240. Well, at 240 degrees, I'm going to have the same exact representation. But now, once again, I'm going to think about a coordinate plane. Notice how on the left side, I was negative positive with my x. If I was in quadrant 3, I'm thinking, okay, I'm negative with the x because I'm left. I'm negative with the y because I'm going down. So this particular coordinate just has to be a negative 1/2 and a negative square root of 3 over 2. Okay, so see how I can build everything around this triangle just with our first quadrant. Technically, I could do this with any triangle within this problem. Okay, let's just continue on. Let's just say I want to start a different triangle. And let's just show how great this stuff is. Let's just say let's do a different reference triangle and let's try to apply the same knowledge. If I take my 45-degree triangle, which looks similar to that, let's say I flipped it over the y-axis to get this here. Same exact picture, both 45 degrees. At that point, that would be at my 135-degree angle. Well, if I'm referencing how is that going to change based off of my coordinates? Well, I want to think about a coordinate plane. The values have to stay the same. The only difference now is I'm flipping it based off what I see. So this value has to be in the second quadrant, which means a negative x value and a positive y value. And I can build everything off of what is in the first quadrant by flipping those reference triangles all the way around. Okay? So we're using a little bit of everything. We're using geometry based on special right triangles. We're using our algebra skills to help derive these values out, finding our radians, things like that. And what we do is we develop this ultimate reference of a unit circle. Okay? And that's kind of the ultimate idea that eventually we are going to build off of and actually use within this lesson. Now, personally, if I tried to write all these out because of my handwriting and things like that, I would have this very messy unit circle. So what we can easily do is go to any website. Let's say I just go to Google and I type in unit circle. It'll literally pop up for us, giving us images of each and every opportunity that we can use. Now, I would highly suggest creating your own unit circle or going around, but understand I could go to any picture on Google and literally get these references out of there. Okay. Notice how all these different pictures pop up, and I can show each of these within a problem. In this case, I can show each of the coordinates along with the radian measures of each one. Okay. Now, the last important thing I want to bring up, I'm kind of everywhere right now. The last important concept I want to bring up is at my zero marks, so my 0, 90, 180, 270, and 360, what happens to our angles? Because that's another important concept. So let's quickly talk about that. So what we want to discuss is what happens at this coordinate. What is my actual coordinates for those? And you probably saw based on the unit circle I just showed, I probably should talk about it on me, but let's discuss why this happens. Well, at the 0 mark, technically you have the coordinate 1, 0. And the idea behind that is if you really think about this, this here is considered to be my radius, and we talked about how in a unit circle, the radius is going to equal 1. Well, I can't build a triangle off of a line. So what that's representing is you have a horizontal line equal to 1. And horizontal lines usually represent the x value. So technically in this particular problem, you have an x value with no y value, so you have to have a 1, 0 coordinate. Versus if I take that same idea into my x value, or excuse me, at the 90-degree mark, I have a vertical line with the same representation. My radius equals 1. So at that coordinate at 90 degrees, I have to have a coordinate equal to 0, 1. Because I'm positive in the y-axis, I'm up 1, and I have that coordinate there. Okay? Now, I'll be posting an actual unit circle within the classroom for you to use at all times, an opportunity for you. Today's video was just strictly talking about how we're actually going to represent it. In tomorrow's class, we're literally going to talk about how we actually use the unit circle to our advantage. Okay? But besides that, I'll leave you at that. Have a great day. We'll be talking about this tomorrow, and I will see you in class.